Binary tree. This is an interesting memory construct, or at least interesting idea. I will begin with a picture. It looks like this. Every circle represents a node. A node is like a place where you can store something. For example, maybe we can store a number in every node. And we mark the sons of every node in this tree with those lines. For example, for this node, the two sons are this node and this node. And maybe, for example, for this node, the two sons are this node and this node. So basically every node has at most two sons, maybe a left one and the right one if we want to consider directions. You might be wondering, why would anyone want this kind of thing inside his program? Binary trees are very useful in many algorithms. Maybe if you are not an experienced programmer, or maybe if you didn't deal with many algorithms in the past, then you are not familiar with this structure. But it is very common when programming things that should work fast. We might see it again in the future. At this point, I don't want to deal with what we can do with a binary tree. I want to deal with how to represent it using linear memory. Just as an example of what we can do with our linear memory. Let's begin by numbering the nodes. Pretty much as usual. We always do it. We always number the nodes in some way, and then we use those numbers as a way to flatten the structure. This will probably be the first byte, and this will be the second byte, and this will be the third byte in the bytes array, just as an example. Finally, we flatten the tree into linear memory, just as we proposed. We leave an empty space. The 0 location is going to be empty. We will soon find out why. And we store every node into the location which is determined by the number of this node. For example, node number 1 is going to be in byte number 1. Node number 2 will be in byte number 2. If we are talking about bytes, for example, it could be D words if we wanted. We could think about those cells as D words. Now that we put everything inside this linear structure, how can we use the tree? Because we might want to know which cells are the sons of 4. Every cell corresponds to some node, so we want to be able to get the sons, for example, or maybe the father of some node. So how can we do it? Let's look at an example of 4. 4's sons are 8 and 9. It is not so hard to find out that the children of 4 are just 2 times 4 and 2 times 4 plus 1, which are exactly 8 and 9. We can just, for example, check some other number, for example 6. 6 sons are 6 times 2 and 6 times 2 plus 1, which are exactly 12 and 13. And we can see that this rule applies to every node. We can use this rule and conclude that k's sons are 2 times k and 2 times k plus 1. By the way, if we want to get somebody's father, for example, who is the father of 10, we can just divide 10 by 2 and we get 5. Maybe another example, who is the father of 15? We divide 15 by 2 and the integral result is going to be 7, which is the father of 15. Even though we flatten everything into this array of containers, which looks pretty simple, we are still able to find out the sons and the fathers. So we managed to preserve the construct, to preserve the binary tree construct. Let's look at some actual code of something that we can do with the tree. We are going to look at a very simple example, just traversing the tree in this manner. We just take the left every time. We take the left son of every node and then we continue by taking the left son. First, the representation of the tree in the memory. We define tree size to be a constant, which will represent the size of the tree. Here the size is 15. And then we define this linear memory construct, which is just going to be tree size plus 1 D words, which is exactly 16 D words in this case. Next, we look at the code that actually does this kind of traversal. We load the label myTree into ESI and 1 into ECX. 1 is going to mean the root. You might be wondering why we have plus 1 here. I remind you that the first D word is unused. We are not going to use D word number 0. Therefore, we add 1 for this unused D word. We set ECX to be 1, which means that we begin from the root. We are always going to look at ESI plus 4 times ECX. And we never want ECX to be 0 because the first D word at location myTree plus 0 is unused. Therefore, we begin with 1. So this is the root. Every time we are going to print the contents of the current node, and then we are going to calculate the left son's location in this array. We read the contents of the node by just reading the memory, ESI plus 4 times ECX. The 4 is here because this array is array of D words, and every D word is of size 4. Next, we print EAX. Now it's time to calculate the next node, the left son's location. We do it by calculating 2 times ECX. We use the LEA instruction to do it. We could, for example, do something else, like maybe shift left. It would work too. Next, we compare ECX to tree size to make sure that we didn't go out of the boundary of this memory construct. And we move on to the next son, which means that now we are going to print the contents of the son. We began with 1, we printed its contents, then we move on to 2, and we print its contents, and so on. The output of this program is going to be 1, 2, 4, 8. I want to show you a little modification of this code, which gives a different result. Make sure to look at this instruction, LEA ECX 2 times ECX. I just added 1, and I got a different result. Instead of finding out the left son's location, now I find out the right son's location, which means that I'm going to print 1, 3, 7, and 15 to the console. I think it is pretty cool that you can make such a small modification and get such a different result. It also shows the power of the LEA instruction, which allows you to just add 1 with the bracket syntax. Summary. We have seen the following memory constructs: array of structures, 2-dimensional table, and binary tree. Much more could be achieved. This is really the beginning of what could be achieved. Probably the reason that we couldn't see more is because our assembly skills are not strong enough at this point. We still have to improve them to see more advanced examples. I want to remind you that whenever you want to use the memory to store some complex construct, you will have to use your imagination. You will have to think a little. What would be the right way for you to put this construct in memory? Usually there is more than one way, and every way is good for another occasion. Exercises. As usual, there is some code reading and code writing. You will also see some bonus exercises. Have fun!